In this video, we discuss learning outcome number 5 from lesson 10.2, which is about residuals and the least squares property. My goal for you is this. By the end of this video, I hope you'll be able to explain the relationship between residuals and the regression line. In your own words, I'd like for you to be able to describe what we mean when we say that the regression line is the line that best fits the data. So to start, let's define this term residual. For a pair of sample X and Y values, the residual is the difference between the observed sample value of Y, or the actual sample value of Y from our sample, and the Y value that is predicted by the regression equation. Or in other words, the residual is the actual Y value that we see, that we observe, and minus the predicted Y value from the regression equation. It's just the Y value minus Y hat. So I have a very small sample here. I've got 4 ordered pairs, X equals 8, Y equals 4, X equals 12, Y equals 24, and so on. So we have this very small sample, and we're looking at this particular point, X equals 8 while Y equals 4. So I'm just focused right here. It turns out that this sample of 4 data points has a regression equation that's very simple. The regression equation is just Y hat equals X plus 1. So if I know that X is equal 8, and I want to know what the regression equation predicts, well, then I just plug in X equals 8 to the regression equation, and I say that my Y value ought to be something like Y hat, which is 1 plus 8 or 9. So the regression equation is predicting that Y is equal to 9 when X equals 8. But meanwhile, we see that in our data set, when X equals 8, the Y value is not 9, the Y value is 4. So that is the observed value of Y. I like to call it the actual value of Y. It's the Y value from our data set. The residual is the difference between this Y value from our data set of 4 and the Y hat value predicted by our regression equation of 9. The difference between Y and Y hat is -5. I think that's easiest to see when we look at the plot right here. So if Y is equal to, if X is equal to 8, so we're right here at X equals 8, the data point is at this location, X equals 8, Y equals 4. So that's our point. Now the regression line is this line right here. The Y value that is predicted by the regression line when X equals 8 is Y equals 9, which is exactly what we see on this graph. So the residual is the difference between this Y value and that Y value. Since this Y value is higher, the difference is negative. So the residual it's like the distance between those 2 points, but it's signed. If the point lies below the line, the residual is negative. So here's another point that lies below the line. This must correspond to X equals 20. When X equals 20, this regression equation predicts that Y hat is equal to 21, or predicts that the Y value would be 21. When X is 20, Y is 21. That's what the line tells us. But it turned out that when X was equal to 20, the actual Y value was 8. So we plot the point X equals 20, Y equals 8 in our scatter plot. The difference between this Y value here and this Y value up here on the line is the residual. Since our point is below the line, the residual is negative. When our points are above the line, like they are for X equals 12 and X equals 24, the residual is positive. When X equals 12, the actual Y value in our data set is 24. But the predicted Y value from our model is 12 plus 1, or 13. So the difference between the Y value of 24 that we actually see in our data set and the Y value of 13 that is predicted by our model is this distance. Since it's above the line, that residual is positive. The Y value minus Y hat is 24 minus 13, which gives us that residual of 11. So you can see that we have a residual of -5 right here. We have a residual of 11 right here. We have a residual of -5 when x equals 8. We have a residual of 11 when x equals 12. We have a residual of -13 when x equals 20. And we have a residual of 7 when x equals 24. Again, if you wanted to compute this, you'd say, okay, well, when x equals 7, the observed value of y, the y value from our data set is 32. The question is, or not when x equals 7, when x equals 24, the observed value of y is y equals 32. You might say, okay, well, what should y be according to our regression equation? What does our regression equation predict y to be when x is equal to 24? Well, the regression equation predicts that y is equal to 24 plus 1, or 25. The difference between that 32, the actual y value, and that predicted y value of 25 is 32 minus 25, which is the length of this little line segment. And that length is 32 minus 25, which is 7. That's the definition of the residual. Okay, so now we can talk about the least squares property. If you were wondering why there were all these little squares around here, there's a reason for that, and it's related to this least squares property. This least squares line, or best fit line, is best fit in the sense that it satisfies the least squares property. We say that a straight line satisfies that property if the sum of the squares of the residuals is the smallest sum possible. You might think about that a little bit. So you take all the residuals. So we'll take the -5, the 11, the 7, and the -13. You square those. When you square those, you get a value that's this area plus this area plus this area plus this area. So we'll get 121 plus 49 plus 169 plus 25. You're going to get some value. That is the sum of the squares of the residuals. We say that a straight line satisfies the least squares property if that sum is as small as possible. So what that's saying is, let's say I drew another line on here. Let's say I drew a line that looked like this, and I said maybe that is actually the line. If I were to come up with residuals using that line, so I'd have a residual that looks like this, and a residual that looks like this, and a residual that looks like this, and a residual that looks like this. If I were to take each of those residuals and square them, it's hard to draw, and then square this residual, and square this residual, and square this residual, and add them all together, the sum of those squares of the residuals would be larger than the sum of the squares of the residuals that we have right here, because this is the best fit line. This is the line that will make the sum of the squares of the residuals as small as possible. So that's what we mean when we say that this fits, or this is a best fit line. Sorry, I'm trying to get my cursor back. I'm having trouble. There it is. Okay. That means we're taking these residuals, which is the difference between our actual y value and our predicted y value. And we're trying to make those differences, which we would think of as an error. It's an error between the prediction and reality, the actual y value. We're taking those errors and we're taking them when we're squaring them, and we're saying, what line would we draw if our errors were as small as possible? And then we're saying we want the errors to be small as possible for every single XY pair in our data set. And that is the coefficients of the equation that b sub 0 plus b sub 1 times x. Those coefficients b sub 0 and b sub 1 are the coefficients that cause the sum of those squares to be as small as possible. So again, if you use a different line to approximate the data, the sum of the squares of the residuals would be greater than the sum of the squares of the residuals for this computed regression line. Now we can talk about this more, this idea of minimizing the sum of the squares and using that minimum value of the sum of the squares to come up with formulas for b sub 0 and b sub 1 so that we have the equation of the regression line. All of that can be done using calculus. We do that a little bit in Calculus 3 when we talk about minimizing or maximizing functions of several variables. Um, in this case, the expression that we're trying to minimize is the sum of the squares of the residuals. It turns out that the sum of the squares of the residuals is as small as possible when b sub 0 is given by the formulas that we've already discussed, and b sub 1 is given by the formulas that we've already discussed. So when we say that it's best fit, we're saying we're going to try to make the sum of the squares of those errors or residuals as small as possible. The line that makes the sum of the squares of those errors or residuals as small as possible is the best fit line. So that's the end of that discussion. I'll see you in the next video to discuss learning outcome number 6, which is about a residual plot and how it can be used to analyze correlation and regression results.